We are the senior design team working on developing an autonomous lens cleaning system for CAT. Our team members are Cosmo, Eric, Kyle D, Kyle J, Larry, Alex, and Patrick. The goal of this project is to design a versatile cleaning system for each sensor which will be used on CAT's autonomous machines. These machines are used in remote mining and construction industries. By accomplishing this, we will increase the company's brand reputation as well as the safety for the operators. Our solution must be able to handle a temperature range of -40 to 60 degrees Celsius, as well as a surface interval longer than 8 hours. The stereo camera and lidar are sensors that CAT uses to allow for their machines to be autonomous. The two shrouds pictured are what allows for a device to deliver the compressed air and fluid to the lenses. Inputs A, C, and F are for the compressed air. Inputs B, D, and E are for the pressurized fluid. This is a model that displays both the camera shrouds and the tubing strain relief system attached to the stereo camera. These three components make up the mechanical portion of our final prototype for this sensor. The cleaning activation system allows for a prototype to be isolated from the power through the use of relays. The system uses a microcontroller to allow the user to input commands through the serial monitor to control the fluid pump and compressed airflow. The first video is the system cleaning dried-on mud off the lenses with the compressed air. The second video is the system cleaning sawdust off the lenses with pressurized fluid. Our first conclusion is that compressed air should always be used first in a cleaning cycle, as most contaminants can be cleared with this method. The pressurized fluid should only be used to handle tough hazards like ice or the residual particles left behind from the compressed air cleaning cycle. Second, it was concluded that a simple design was best for the stereo camera. The lenses are all on the front face of the device, which allowed us to use a stationary cleaning system.
The team also created a wiper and fluid system to clean the LiDAR pictured earlier. This included a motor housing which held the stepper motor, a bearing, and a mounting box for the limit switches placed at the leftmost orange rectangle. This housing was connected to a plate which would rotate on the central bearing via an internal gear. The rightmost orange rectangle was a protrusion from the internal gear which would contact the limit switches and change the direction of the stepper motor. This prototype also used a clamshell manifold to direct fluid to spray nozzles placed near the LiDAR and an arm to hold the wiper blade. When these pieces are put together, we can see the motor housing in dark gray, the rotating plate in light gray, the clamshell manifold in blue, the wiper arm in white, and the spray nozzles in green. This prototype also used an electrical system which comprised of an activation switch, two limit switches, a stepper motor, a motor drive controller, and a microcontroller. This microcontroller would act as a state machine based on the code that is shown in the flowchart on this slide. We can see this prototype function in the following video. We have the following recommendations for the camera. Continuing to refine the prototype by modifying the weep hole size and placement in the shrouds, increase the variety in the testing that is performed, and to look into a way to heat the fluid and air before cleaning is done. For the LiDAR, we recommend looking into ways to heat the fluid and further develop the waterproofing of this manifold. The team would like to acknowledge the following people for their help with this project: